Application to Geometric Properties, Parallelograms. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we mastered the algebraic techniques for finding the coordinates of a point that divides a line segment into a specific ratio, and we also looked at the special, simplified case known as the midpoint formula. Now, moving forward into this new subsection, we are going to take those algebraic tools we've already learned and put them to work in a more practical, geometric context. Specifically, we will be applying these formulas to solve complex problems involving the unique geometric properties of a parallelogram. So, let's see how our knowledge of midpoints can help us unlock the secrets of these four-sided shapes. The fundamental geometric property. Now that we've reviewed how to use the midpoint formula and the section formula from our previous lesson, let's see how we can actually apply those tools to geometry. On this slide, we are looking at the fundamental geometric property that serves our secret weapon for solving parallelogram problems. When we are working in coordinate geometry, we rely on a key principle from Euclidean geometry. The diagonals of a parallelogram bisect each other. Now, if that term bisect sounds a bit technical, don't worry. In simple terms, to bisect something just means to cut it into two exactly equal parts. So, what does this mean for our calculations? It means that the specific point where the two diagonals cross each other, the intersection point, is not just any random point. It is the exact midpoint of both diagonals. This is a crucial realization because it allows us to use the midpoint formula we just learned to link the coordinates of opposite vertices together, which we will demonstrate in the next few slides. Mathematical logic. First, let's visualize a parallelogram labeled ABCD, where the vertices are listed in order around the perimeter. As we discussed in the previous slide, the diagonals are the lines that cut through the center. To find these, we connect the opposite vertices. This means our first diagonal connects vertex A to vertex C, and our second diagonal connects vertex B to vertex D. Now, here is the crucial part. Because we know the diagonals bisect each other, the exact point where they cross is the midpoint for both lines. In other words, the midpoint of segment AC must be identical to the midpoint of segment BD. Let's look at this using coordinates. If we assign coordinates to our vertices, where is x sub 1, y sub 1, b is x sub 2, y sub 2, c is x sub 3, y sub 3, and d is x sub 4, y sub 4, we can apply the midpoint formula we learned earlier. The midpoint of AC would be calculated as the average of the x-coordinates, x sub 1 plus x sub 3, all divided by 2, and the average of the y-coordinates, y sub 1 plus y sub 3, all divided by 2. Similarly, the midpoint of BD would be x sub 2 plus x sub 4, all divided by 2, and y sub 2 plus y sub 4, all divided by 2. Since we have established that these two midpoints are actually the same point, we can set these expressions equal to each other. This gives us two very useful equations. X sub 1 plus x sub 3, all divided by 2, equals x sub 2 plus x sub 4, all divided by 2. And likewise, y sub 1 plus y sub 3, all divided by 2, equals y sub 2 plus y sub 4, all divided by 2. We will use these exact equations to solve the practical example coming up in the next few slides. Now that we understand the concept of bisecting, let's translate that into mathematical logic. Real-world application, land surveying. Now, you might be wondering, when will I ever use this in the real world? Let's step away from the abstract coordinate plane for a moment and look at a practical application in land surveying. Imagine a land surveyor is out in the field, marking the boundaries of a rectangular plot of land. Now, remember what we discussed in the previous slides. A rectangle is actually just a special type of parallelogram. Suppose this surveyor has successfully recorded the coordinates for 3 of the corners of the plot, but due to an error or lost data, the coordinates for the 4th corner are missing. Instead of having to physically trek across the entire field to remeasure every boundary line, the surveyor can use the mathematical logic we just covered. By applying the property that the center of the plot is the midpoint of both diagonals, the surveyor can mathematically calculate the exact coordinates of that missing corner. It's a powerful way to use geometry to recover lost information. Now, let's see this logic in action with a concrete, step-by-step numerical example. Step-by-step example. Now that we have understood the theory and the logic behind the properties of parallelograms, let's put everything we've learned into practice with a concrete example. Here is our problem. We are given a parallelogram, labeled ABCD, and we already know the coordinates for 3 of its vertices. Point A is at 1, 2, point B is at 4, 3, and point C is at 6, 6. Our task is to determine the exact coordinates of the 4th vertex, which we will call point D. To solve this, we'll follow a systematic approach. Our very first step is to identify the diagonals. As we discussed in the previous slides, the diagonals are the lines that connect the opposite corners. In a parallelogram named ABCD, the diagonals are the line segments AC and BD. Identifying these correctly is crucial because the midpoint of AC must be the exact same point as the midpoint of BD. Step-by-step example continued. Now that we have identified our diagonals in step 1, remembering that in parallelogram ABCD, the diagonals are the segments AC and BD, we can move on to step 2. Our goal here is to find the midpoint of the diagonal that we actually have all the information for, which is diagonal AC. To do this, we apply the midpoint formula we learned previously to the coordinates of point A, which is 1, 2, and point C, which is 6, 6. We add the x-coordinates together, 1 plus 6, to get 7, and then divide by 2. Then, we do the same for the y-coordinates, adding 2 plus 6 to get 8, and dividing by 2. This gives us 7 halves for the x-coordinate and 8 halves for the y-coordinate. When we simplify those fractions, we find that the midpoint of AC is exactly 3.54. We will need this specific point in the next step to help us find our missing vertex. Step-by-step example continued. Now that we have successfully found the midpoint of our first diagonal, AC dollar, we move on to step 3. In this step, we need to set up an equation for our second diagonal, which is BD dollar. Since we don't know the location of the 4th vertex yet, let's assign it some placeholder coordinates. We will let the coordinates of vertex D dollar be x dollar, y dollar. Now, remember our fundamental rule from earlier. The midpoint of diagonal BD dollar must be exactly the same as the midpoint we just calculated for AC dollar. So, using the midpoint formula with our known vertex B dollar, which is 4, 3, and our unknown vertex D dollar, the midpoint of BD dollar is expressed as the quantity 4 plus x dollar all over 2, the quantity 3 plus y dollar all over 2. We will use this expression in the next step to solve for our missing values. Step-by-step example continued. Now that we have the expression for the midpoint of our second diagonal, BD dollar, we move on to step 4, where we equate the midpoints. Remember from our earlier slides that the fundamental property of a parallelogram is that the diagonals bisect each other. This means the midpoint we calculated for diagonal AC dollar in the previous step must be exactly the same as the midpoint for diagonal BD dollar. So, we are going to set our two expressions equal to each other. For the x-coordinate, we take the expression for the midpoint of BD dollar, which is 4 plus x, all divided by 2, and set it equal to the x-coordinate of our known midpoint, which is 3.5. Similarly, for the y-coordinate, we take the expression for the midpoint of BD dollar, which is 3 plus y, all divided by 2, and set it equal to the y-coordinate of our known midpoint, which is 4. By setting these equal, we have created a system of two simple equations that will allow us to solve for our unknown variables in the next step. Step-by-step example continued. Now that we have set up our equations in the previous step, we have reached step 5, where we actually solve for our unknown variables, x and y. Let's start by solving for the x-coordinate. Looking at our equation from the last slide, we have 4 plus x, all divided by 2, which we know is equal to 3.5. To isolate x, our first move is to multiply both sides by 2. This gives us 4 plus x equals 3.5 times 2. When we calculate that, we get 4 plus x equals 7. From here, it is a simple matter of subtracting 4 from both sides, which leaves us with x equals 7 minus 4, so x equals 3. Next, let's apply the same logic to find our y-coordinate. Our equation shows that 3 plus y, all divided by 2, is equal to 4. Again, we multiply both sides by 2 to clear the denominator, resulting in 3 plus y equals 4 times 2. This simplifies to 3 plus y equals 8. By subtracting 3 from both sides, we find that y equals 8 minus 3, which gives us y equals 5. By following these algebraic steps, we have successfully determined the missing coordinates. Step-by-step example, conclusion. So, after performing those algebraic steps and solving for our unknown variables, we have reached our conclusion. We found that x equals 3 and y equals 5. Therefore, our final answer is that the coordinates of vertex D are 3, 5. This completes our step-by-step calculation for this specific problem. Common mistakes to avoid. First, let's talk about incorrect diagonal pairing. A very common error is accidentally pairing adjacent vertices, for instance, treating the line segment from A to B or B to C as a diagonal. Please, always remember that diagonals must connect opposite vertices. In a parallelogram labeled ABCD, your diagonal pairs must be A with C and B with D. Second, pay close attention to the vertex order. The problem will usually name the shape in a specific sequence, such as parallelogram ABCD. This tells you that the vertices must follow that exact sequence as you move around the perimeter of the shape. If you misinterpret the order, your diagonal pairs will be wrong, and the rest of your calculation will fail. Finally, watch out for calculation errors when finding the midpoint. A frequent mistake is simply forgetting to divide by 2. Now, here is a little tip to save you some time. When you are equating two midpoints, as we did in the previous steps, the denominators of 2 on both sides actually cancel each other out. This simplifies your work significantly, leaving you with a much simpler equation. X sub 1 plus x sub 3 equals x sub 2 plus x sub 4, and similarly, y sub 1 plus y sub 3 equals y sub 2 plus y sub 4. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the logic we used in our example to find vertex D, it is very easy to make a mistake during an exam if you aren't careful. Keep these points in mind, and you'll avoid the most common traps in these types of problems. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. First and foremost, remember the fundamental geometric property we discussed at the beginning. The diagonals of a parallelogram bisect each other. This is the golden rule for all the problems we've tackled today. Because they bisect each other, this leads directly to our most useful algebraic tool. The midpoint of one diagonal is exactly equal to the midpoint of the other diagonal. If you can find the center of one line, you've found the center of the other. When you are faced with a problem where a vertex is missing, just like the example we worked through step by step, your strategy should be this. First, calculate the midpoint of the diagonal where you already know both endpoints. Then, use that specific point to set up your equations and solve for the unknown coordinates of the second diagonal. Finally, if you want a quick shortcut for your calculations, you can use the general relationship for the vertices of a parallelogram, A, B, C, and D. You don't even need to divide by 2 if you use the simplified form. X sub A plus X sub C equals X sub B plus X sub D. And similarly, Y sub A plus Y sub C equals Y sub B plus Y sub D. This is essentially saying that the sum of the coordinates of the opposite vertices must be equal. Keep these points in mind, and you'll be able to navigate any parallelogram problem with confidence.